Hey everybody, it's time to put it all together. So over the course of the past week or so, we've been thinking a lot about bivariate relationships between variables. That is, do we have some sort of independent variable, some sort of dependent variable? What is the overall basic association between these variables? We've thought about some tools like the correlation coefficient and the crosstab, some other different kinds of tools, the t-test and the f-test, that allow us to assess from just a very basic perspective whether or not those two variables tend to sort of go together, whether they're associated. However, now we want to turn to a new tool in our arsenal that will allow us to better estimate these relationships, not in a bivariate way, but we can say in a simultaneous simultaneous relationships between data. And so what this really gets us into is the world of regression. Now, you can certainly read about some of the sort of basic statistical understandings of what regression is and what it does in the Forestier book, and I certainly encourage that. I'm going to be trying to walk you through some of the most essential sort of details of regression in this tutorial, simply by talking you through the way that it's supposed to work from the perspective of sort of a couple of very simple features of the regression model. And so the output things that we're really most concerned about, most interested in looking at, are the significance of a relationship in a regression model, the magnitude of the relationship as estimated by what's called the coefficient, the directionality essentially of that relationship. These kind of three things, right? Strength, significance, and directionality. Strength also as another way of saying magnitude. Right? These are the things that at the end of the day we want regression to be able to tell us. So the logic of regression, though, this is why it's so much more powerful, I think, than some of these bivariate tools, is the idea that we can estimate this relationship, the IV-DV relationship, in the presence of other relationships in what's known as a data space, which then allows us to say things with more credibility than we would otherwise. So to estimate simultaneous relationships, the first thing that we want to do is, of course, make sure that our handy tidyverse is installed, and a new package that we probably don't have installed yet called Stargazer. You can go up to Tools and Install Packages. You can type in Stargazer into this box and install it if you don't have it already. Make sure that both of these packages are installed and loaded into your data space to be able to do this module. The first thing I want to do is, of course, I want to load in my data. So the data set that I'm going to use again is this familiar, very basic data set called TapList, which is just 32 observations of a bunch of different descriptions of beers. We can use head TapList here to get a sense of what it looks like again. Right? Remember, we've got the name of the beer, we've got the type, the size in ounces, the alcohol by volume as a percentage, the origin, the brewery, price, and we've got a couple of binary variables that I coded last time. We've got whether the beer is dark or light, and then we've got whether the beer originates in Maryland or whether it does not originate in Maryland. So the first thing I want to do is construct a regression model for the very first time and introduce you to the syntax of a regression in RStudio. So, of course, every time we're creating anything in RStudio, we're generally using an equal sign to create an object. I've actually already created this object because I've already run this code, but what I'm going to create here is a thing called mod0. I like to call it mod0 because this is a model, a regression model, in which we're simply just creating the bare bones structure of the model, and we're not putting anything in here yet that will allow us to examine any kinds of relationships. What this is doing is, I think, just showing you, I'm going to make this mod0, that's a typo, I want to show you what this regression output looks like before we actually model anything. So this is sort of the bare bones shell. It'll allow me to talk a little bit more about what the regression is and sort of why it matters. So this model, we use the LM command. LM stands for linear model. We want to make sure that we've got the data here indicated. So the data is TapList. That's the data source that we're using, this flat rectangular data set. In this case, let's imagine that I want to know, that my burning research question is, what makes beer expensive or cheap? Okay, maybe I'm a cheapskate. I want to figure out how to get the cheapest beer. And I want to know what are some of the variables, what are some of the factors here that predict whether a beer is expensive or inexpensive. So the first thing to do is I want to make sure in this little formula that I've created that I've got price as the dependent variable on what's called the left-hand side of the equation. This little tilde here, it's a little tilde key that's on the far left side of your keyboard. That tilde is essentially separating the left-hand side of a regression equation from the right-hand side. And right now I have the right-hand side has nothing in it. It just has a 1 here. I put the 1 in here as just a placeholder to indicate that it's going to be creating what you can read about in the book is known as the intercept. So if I run this, you'll see that I get from this summary command a summary of this linear model. We'll see the formula has been repeated here. We know where the data is coming from. Don't worry about this right now. This is not something to look at really in detail. What we want to do instead is look at this coefficients output as the first thing to look at. And the first thing we see here is that there's only one row in this kind of little, what will eventually become a little table. You'll see that you've got intercept here, you've got estimate, standard error, t-value, and then this thing, PR greater than absolute value of t, whatever that means. So what this is essentially is this table is going to be the number one thing that we want to look at in an R regression output, which tells us something about, again, the strength of a relationship, that is the magnitude, the significance of the relationship, whether or not this relationship is likely to have occurred by random chance alone, or whether there seems to be some sort of reliable association, and then of course the direction of that relationship as well. And so the magnitude here is essentially this estimate. The magnitude can be interpreted very basically in this first shell of a regression model as essentially this is what happens. This is essentially the average. In the empty shell regression setup, this estimate of the intercept is essentially just the average price of a beer. As you can see that the average price in our tap list is about $6.45. Remember, these are listed as prices that are in US dollars. So it's a very interpretable thing. And we can see that there's a standard error here, which means that basically most beers are within basically 2 times this estimate. So a fairly expensive beer in our data set is going to be about $7. A fairly cheap beer is going to be about $6, more or less. That gives us a sense of the spread of the data. The t-value is a statistic which comes from a t-test. It's the exact same t-test that we were describing last time in our bivariate relationships. And we can see that what that t-value does is it really doesn't tell us anything. All it does is it allows us to compute a p-value. And so you'll see, again, this p-value is listed in scientific notation. This is why we get this e minus 16. You probably remember this from graphing calculators long ago. So what this is really telling us, we can calculate this, is that this p-value is essentially less than 3, 4, 5, 6, 7. It's really, really, really small, okay? It is less than, I guess, 2. It's really small. Less than 2, some trillionth or whatever of a point here. All p-values range from between 0, they're bounded by 0 and 1. And in this case, it's extremely, extremely close to 0. The smaller the p-value, the more likelihood, the more credibility we have in saying this, ultimately that this relationship that we're observing is unlikely to have occurred by random chance alone. In this case, this p-value is simply reporting this estimate's likeliness to have occurred by chance alone. And what it is testing is whether or not this estimate is it could potentially include 0. So I like to use, again, the beer data to tell you about this, because what this is really telling us is that this is a test of whether or not it's credible to assume that the average beer is free, that the average beer costs $0. Well, does the average beer cost $0? No, it's at least $6.45 away on average from 0, as in the beers cost money. And so this is saying that it's extremely unlikely that the beers are free at this restaurant. And of course, that makes sense, right? The beers are not free at the restaurant. They cost money. And in fact, we're estimating that they cost this much, and we are very, very, very confident that they do not cost $0. So essentially, this estimate is floating somewhere far above 0, and we're very confident that it's not going to be actually 0. To further investigate these quantities, let's build in, for the first time, a bivariate analysis in our regression. So what I'll do is I'll put in an independent variable. Let's say that I think that beers that have higher alcohol by volume concentration are going to be more expensive. I guess the logic here, the theory is that brewers, I guess maybe it takes longer to brew a really high alcohol beer, or maybe it takes more hops, more yeast, more raw ingredients, I guess. And so to make this really boozy beer, it actually costs the brewers more, and so they have to then charge more for the beer. That's maybe my working theory. And so I would expect that there'd be a positive association, right? We could say my hypothesis. In a comparison of beers, I hypothesize that an increase in alcohol by volume will be associated with an increase in price, all else equal. So what I can do is I can actually formally test that hypothesis using the regression model. I can take this, I can highlight it, I can run it. You see again, I've created this object called mod1. Now I want to say, hey, now that I've created it, let's summarize it so that we can look at it and see what it says. And we'll see again that we've got the formula and everything. We've got this thing that you shouldn't look at right now. It's not important. Our table has now grown by 1 row. We've got that intercept again. Interestingly, we'll see that the estimate has changed a lot. That's kind of interesting. But now we've got this new one with an estimate that's much lower. It's 0.4064. We've got 2 probabilities here, right? 2 p-values that have been reported in the data. And we've also got these stars, right? The stars, actually, the significance codes here are identified here. So the stars essentially are telling us, this is right here, right? This is saying that with 3 stars, that this p-value is lower than 0.001. It means it's very, very small. And again, a very small p-value means we have a lot of confidence. Small p-value, a lot of confidence. That this estimate does not include 0. And so again, previously we were pretty confident that this estimate up here of the average beer price did not include 0, beers aren't free. Here again, we see that even though this estimate is much lower for a specific reason, once again, we're pretty confident that the average beer does not cost 0. ABV is what we are most interested in thinking about now, though. This is the actual independent variable. For the first time, we're able to estimate a quantity that allows us to say something really meaningful about the effects of ABV on the price of beer. And so what this effect tells us, ultimately, we can interpret this in the following way. Okay, and I'll even write this out here at the end of the summary so that we know. So we can say, well, I guess not all is equal yet, but we can say essentially a 1 unit increase in alcohol by volume. Okay, so what is the unit here? This is a 1% increase. Is associated with a 0.406, so 0.41. We can round up. 0.41. What is that? 0.41. Oh yeah, that's right. It's dollars, right? 0.41. So a 41-cent increase, and this is a positive coefficient. This is not negative. 0.41, 41-cent increase in the price of a beer. Okay? So that's really, really kind of an amazing statement, because for the first time we can say here, look, 1% increase in ABV is associated with, so for every percent, as my ABV goes from 5% to 6%, our beer is expected on average to get 41 cents more expensive. So if I had a 15% ABV beer, we'd expect it to be really expensive, right? In fact, we can even calculate this on the basis of these averages. We can calculate the price of a beer. So let's imagine, right? How expensive is a beer? Well, it's on average going to be, we use this intercept. So what this becomes is, this estimate, this is the expected price of a beer if the ABV is 0. Okay? And that's why it's really low. It's kind of interesting. So if you had a non-alcoholic beer, I guess, according to this data, the beer would be $3.88. And so what we do is we take that $3.88 and we multiply it by, let's say we've got a 6% alcohol by volume beer. 6% times 0.41. Okay? Of course, we can do that really easily in R. We've got a little calculator here. 634. So on average, we would expect that a 6% ABV beer is going to be 634. However, a 12% ABV beer, how much is that going to cost? A lot more, $8.80, right? because we're simply multiplying the number of ABV, the ABV percentage, by that estimate. Every single unit increase, so it's a linear model. Every unit increase, 1% increase in ABV adds another 41 cents to your average beer. And so that's what we can interpret from this model. It's a really powerful statement. And of course, the reason we're able to say that is the p-value. We're able to then say that, and that's because, again, following these stars, because this is, with scientific notation, this is a really tiny value. Following these stars, we know that this is less than 0.001. So we'll put here, p less than 0.001. This is the kind of statement that could go in my paper to interpret the effect of an independent variable. And so what does this mean in general? Well, what it tells us is there is a positive association between ABV and price. And in fact, we can augment this, right? There's a strong positive association, strong, significant, right? This is statistically significant because the p-value reports that it's very small. It's under what we would consider to be a standard threshold for significance of 0.05. So this means something. ABV has a meaningful, robust effect on price. However, remember, we might have some intervening variables that could do things to this estimate. Like for one thing, I mean, I threw Maryland in here. I don't know what the theory is about Maryland beers, but what about light beer, right? Light beer could be an intervening variable. This could have an influence on whether or not the beer is expensive, and it could also have an influence on whether the beer has high alcohol, right? This could actually be something that we want to control for in the model by including it simultaneously, right? This is the idea of simultaneity in a regression model. We want to include all of these variables, this one being continuous, this one being binary, and this one also being binary in the model, and then be able to interpret that coefficient again and see if maybe those coefficients change. So I'm going to go ahead and do that, select that, and run it. And we'll see that now, again, our little regression table starts to get bigger. We've added additional rows. Now, one thing that you'll see that's very interesting is that this thing kind of spits out some junk here, right? It says Maryland, not Maryland. What does that mean? Well, what it usually will do is, if you've got a variable that's described in your data as, this is called tap list. If you've got tap list in here, you'll see that these are characters, and we've got these things that are the descriptive labels and not ones and zeros. What this tells you is this is the effect of moving from Maryland to not Maryland. Okay, this is the effect of being light as opposed to dark. This is the effect of being not Maryland as opposed to being Maryland. And so whatever comes after the variable name, right, this is essentially the effect of that status on the outcome if you're in this categorical world. And so we can see is, first of all, there is some positive association between Maryland and price. However, this p-value is 0.15-ish. And what that's telling us is that this is far above, this is bigger than this last star, this last threshold for statistical significance. So what it tells us, what this really says is that even though this estimate is positive and it seems to be of a large magnitude, we can't interpret it because the p-value means that it's not likely to have been the product of anything other than random chance. Okay, it's something that's happening, and we simply put, right, there's a very specific language that we need to use to talk about probability here, but at the end of the day, I think for our purposes, one way that we could conceive of this is we just don't have enough confidence to be able to say anything meaningful about this estimate. And so even though the estimate is seemingly large, it seems like Maryland beers not Maryland beers, beers from outside of Maryland are about 51 cents more expensive on average while controlling for these other factors. It's not something that we can make a strong statement about. Similarly, light beers seem to be a little bit cheaper on average, about 9 cents cheaper. But again, this probability, right, it's very unlikely that this effect is anything other than zero. There's no way that we can really interpret this coefficient or its magnitude or its direction. So what we usually do is we essentially say there's not enough evidence here to be able to conclude anything about the strength or the significance, or excuse me, the strength or the direction of these associations. Lastly, though, we'll see that the ABV coefficient, the estimate, has actually changed a little bit in the presence of these variables. So one thing that we see is that it has remained significant. It's still less than 0.05, which means that we still can interpret it as being this positive, strong association. So we can go up here. I'm going to grab my same text here, and I'm going to add something important here. all else equal. Okay, a lot of economists write ceteris paribus. It's just Latin for all else equal. We can say all else equal, a 1% increase in alcohol by volume is associated with this coefficient's changed, so we have to update this, right? 46-cent increase. It's actually gotten larger in the presence of these other factors. In the price of a beer, in this case, this is no longer 0.001. This is actually 0.01, right? So 2 stars. It's less than 0.01, so it's pretty small still. Pretty robust finding. So we can say that there still is a strong, significant positive association between ABV and price in the presence of state origin and light-dark classification. So even with these other variables, these potential threats to validity, we see that that relationship still holds up. This is where you want to be with your analysis. This is the goal, ultimately. You want to be able to make a statement that is bolstered by a significant relationship here with the p-value about the magnitude of the effect of your variable on the outcome. Now keep in mind, right, if this were negative, that would be a negative association. We might say that ABV decreases price. But of course, in this case, because that makes sense, it's positive. Okay, the last thing that I want to show you here in this discussion of regression is we can use another package, the Stargazer function, to be able to look at these models side by side. So we can use Stargazer here. We've got mod 0, mod 1, and mod 2, which are all objects that I've created one by one in this tutorial. I can look at them together. This is what's called an analysis of nested models. And as long as you basically have the same thing where you're building this model out, you're starting with price with nothing, then you're adding your IV, and then in the second model you're adding some control variables, you'll be able to see this take the shape using the type equals text option, take the shape of a very pretty little table. I'll pull this up so we can see it, the whole thing. You can see here we've got model 1, model 2, model 3. We've got our ABV, our alcohol by volume here, which is included in models 2 and 3. We've got our control variables, which were included only in model 3. And we've got the constant, which is included in all 3 models. We can see that the observations, there are 32. And we can also finally see a really important statistic, which is a fit statistic called R squared. So you can read again more about R squared in the book. But at the end of the day, what R squared is essentially telling us is the proportion of the variation in the dependent variable that we can explain using the presence of these combined variables. So essentially, if we've got these nested models, we can essentially say how much of the outcome, how good are we basically at explaining the variation in the outcome. And it turns out that ABV alone, just having ABV in this model, we can see R squared increases a little bit. Adjusted R squared is a metric that accounts for the number of variables that we've got in here. So it's a little bit more conservative. But if we just use R squared as the basic measure, even though this increases a little bit when we put in these other variables, we can see that ABV alone is accounting for about 45% of the variation in price. Meaning that if we had to guess how expensive a beer was, and you said, okay, well, can I at least know the ABV? We would do a lot better at guessing the price if we knew about ABV than if we didn't. Here, of course, we have no predictors in the model. We just have the constant, and so the R squared is 0, meaning that we can't predict things at all. We can just guess the average. If we had an R squared of 0, we'd say, okay, how expensive is a beer? I'm going to guess it's $6.45. And we'd be wrong sometimes, we'd be right sometimes. Here, we'd be able to use that simple little heuristic that we plugged in, right? That simple little formula. We'd be able to make a guess about the price of beer that would get us almost halfway, right? We'd improve our guessing, right, by a substantial amount as a result of this model alone. If we knew all of these things, we'd be able to get over half of the explained variation in the price if we were trying to predict another beer's price. But altogether, again, this is a really nice little table that Stargazer creates. You can take this out, you can copy this out of the R console, you can paste this into a document. In a later video, I'll show you how to take this, use Stargazer to actually dump out an even prettier table that can then be pasted into your Word documents for analysis. But for now, this is a really nice, neat way to examine the regression output. Because again, we've got here the coefficients, we've got standard errors, which looks at the sort of credible interval within which this thing sits. We've got the stars, which of course reflect the level of significance of each of those. And we've got the directionality, whether they're positive or negative. And so for each of these models, right, model 1, 2, and 3, and the nested analysis, we get a really good feel for the relationship. So this is one of the reasons why regression is such a powerful tool. It's a one-stop shop for the strength, the significance, and the direction of a relationship. And it allows you to write these really nice statements when you interpret those regression coefficients that can go in your paper that give you a definitive answer to the hypothesis that you've set up in composition 4. So with that having been said, I leave it to you to start playing around. Once you've got your data in here, start running these regressions, see what happens, see if you break it, see if you get a result, and we'll start interpreting some coefficients. So long.